Okay, so let's go ahead and take a look at 7b here. So in this case, we are wanting to add together the first five terms. So j is 1, meaning we're going to start at 1. The end value, or the top, the upper limit is 5, meaning we're going to end at 5. So what we want to do here for b is we want to take a1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. And so for this problem, if I'm going to go ahead and substitute in the corresponding values, my variable is j, so I want to substitute in 1 for j, which would be 1 over 1, which is 1. 2 in for j would be 1 over 2, then 1 over 3, and I would follow this pattern, 1 over 4, and then 1 over 5. So then I can evaluate this. If you want to do this by hand, that's fine, but it's probably a little bit easier to use the graphing calculator for this. So I'm going to have 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth. That's going to give me a decimal here, so if you wanted to write this out as 2.283 repeating, you can. But I'm going to go ahead and convert that to a fraction. So the exact answer here would be 137 over 60. So the summation here, the series for the given sequence from the first to the fifth term would be 137 over 60. Let's go ahead and take a look at C. C is a little bit different because for the first time we have a term that does not begin, or the series does not begin at 1. This has a lower limit of 3. So when I'm computing the summation in C, I'm going to have a sub 3 as my starting location. So I'm going to have a sub 3, a sub 4, a sub 5, and then a sub 6 is my ending location. So it's not all summations begin at 1. It's common that they do, but sometimes they don't. So in this case, it's going to be start at 3 and end at 6. So I want to find those individual terms. I'm going to use my calculator here because this may be a little bit more difficult. So negative 1 to the third power times 3 squared would give me negative 9 for my first term. My second term is going to be negative 1 to the fourth power times 4 squared, which is 16. Then I'm going to have negative 1 to the fifth power times 5 squared, which is negative 25. And then if I keep this pattern going, you could type that in, but if you see the pattern here, this is going to be positive 36. So when I add all these together, the series, summation, is 18. So this specific one, we do have to pay attention to the lower limits and the upper limits. The specific one starts at 3 and ends at 6 in those summations. Now we can also go the other direction. We can start with, sorry, here, scroll down here. We can start with a summation written out in terms and then write that into summation notation. So summation notation again is this sigma symbol. It looks kind of like an E. So what we need to do is figure out where does this one first begin. So we're going to go ahead and assume this starts at the first term. So it doesn't matter what variable we use. I'm going to use the variable 1, or n, sorry. So n equals 1. And I can see that there's 5 total terms here. So let's go ahead and end this at 5. Now, if I want to see what's happening to the pattern here, so I notice this is an odd number 1, an odd number 3, an odd number 5, and 7, 9. So we see that the pattern is just a summation of odd numbers. So odd numbers can be found by taking any even number, which is anything that's a multiple of 2, and subtracting 1. So if you took like 2 and subtracted 1, that gives you an odd number. If you take 3 and subtract 1, that gives you, 4 and subtract 1, that's an odd number. 6 subtract 1, that's an odd number. So this would be our summation notation here. So 2n minus 1 represents this value. So 2 times 1 minus 1 is 1. 2 times 2 minus 1 is 3. 2 times 3 minus 1 is 5. 2 times 4 minus 1 is 7. 2 times 5 minus 1 is 9. So this would be our summation notation to represent this expression. taking a look at B, B is similar, but has some differences. So again, this is a summation here. We may assume this one's going to start at 1, so I'm going to go ahead and start it at 1. One thing that we notice here is that this one has 3 terms, but then it goes on forever. Sorry, I wrote down a 2. It has 3 terms, but then it goes on forever. So this one actually is not going to have an ending. So we're going to put a little infinity symbol up there on top of the summation notation, showing that it's going to continue endlessly. Now, what I may notice here is that each of these are a multiple of 3. So this is 6, 9, 12. We would assume the next number is going to be 15, 18, 21, and so on, which would follow the sequence that we have here. But the issue with this in our summation notation is, remember there's a multiple of 3 before this. This one should start at 3. If we think about this sequence being a multiple of 3, 3 is the first multiple of 3. So really with our summation notation, what we have here is that this is actually skipping a value when we're adding. So we're not starting at 1. We're actually going to start at 2 here. And then every summation is just going to be a multiple of 3. So 3 to the n power. So 3 times 1 is 3. That's not shown there because we're not starting with the first one. But 3 times 2 is 6. 3 times 3 is 9. 3 times 4 would be 12. 3 times 5, 15, so on and so forth. So we have a good summation here. Let's go ahead and move on. So what we can do here, we can evaluate summations like we did, and we can write summations based on expressions. And we can also find different ways to evaluate summations. So sometimes there's some shortcuts. So if you remember back to exponentials and logarithms, we had some properties that had allowed us, to rewrite some expressions. And so we're going to do the same thing for summations. So let's say this is for any constant C. So C is a constant value. It's going to be a real number. So we can add that in there if we want to. If I have the summation of, let's say, k from 1, has a lower bound of 1, an upper bound of n, could go on for however many we want. And we're finding the summation of c. We could have a shortcut here. Instead of actually adding all the terms together, what we could do is we could multiply the last term, or the number of terms, times c, and that would give us the summation of these. And we could prove this, but we're not going to. We're just going to kind of go with it. If you want a proof for that, I can give you one. Just let me know. We could do the same thing for some other examples. So there's some other properties. Let's say that we have the summation starting at 1 and going into n again of, let's say, an expression c, so a constant, times a to the a sub k. So there is some value with the variable and it's times c. What I can do is I can take the summation of a first, a sub k first. I can do the summation part first, and then I can multiply by c. And then let's say I have another summation. This one starts again at 1, and let's say it goes on to n. And let's say there's 2 parts to this summation. There's an a sub k, and it's either plus or minus b sub k. What we can do there is we can find the summation of each part separately. So we can find the summation of a first and the summation of b first, and then add those together, or vice versa. We can go the other direction. So we can use these properties to help us simplify things. There's a couple more, but these are just the ones that we're going to focus on. Now let's take a look at why we may want to use these properties. You don't have to, but why you may want to. Let's take a look at 9. It says recompute the sum, the summation of 3i plus 2, starting at 1 and ending at 4. So the first 4 terms for the sequence 3i plus 2. And we can do this. We did this actually on problem number 7. We did this by adding all the terms together. Now you can do this by actually using the properties. So what I may notice here is that I'm going to take the property number 3, and split this into 2 different summations. So I can split this up as the summation from I starting at 1 and ending at 4 of 3i, and the summation of I starting at 1 and ending at 4 of 2. Now I could use property number 2 here as well. So notice that this is 3 times I. So what I can do here instead was I can take the 3 out and find the sequence that's I from 1 to 4, the series, sorry, of I from 1 to 4, and then multiply by 3. I can also use the first property for this second term here. Because it's a constant, instead of adding successive terms, what I could do here is just take the n, 4, times the c, 2. So I could rewrite this as 2 times 4. And now this gives me a different way to solve the problem. So this would be 3 times, if I goes from 1 to 4 and it's just I is my sequence expression, this would just be 1 plus 2 plus 3 plus 4 plus 2 times 4, which is 8. So 1 plus 2 plus 3 plus 4 is 10. 3 times 10 is 30. So this is 38. So this is the same answer that we got in 7a, but it's just a different way to work it. Now this may not be easier necessarily if you had to write out all this work, but if you could quickly mentally go from here to here, that would be a pretty quick shortcut. So we have some summation properties that we can use. You don't necessarily have to use them, but they're there available to you. Finally, the last thing that we're going to do is take a look at where sequences can be used. So let's take a look at problem number 10. It said Jack already owned 1,420 shares of a stock when he got the opportunity to purchase 175 discounted shares per year by working for the company. In A, it says if he made no purchases other than these discounted shares per year, how many shares will he have 9 years later? Now, finding the answer to this algebraically step by step for 9 years is probably not that big of a deal. But in B, it says if this trend continues for 25 years, that Jack will work with the company, how many shares will we have when he retires? We probably don't want to do this 25 times. So what we can do here is we can set up a sequence, and then from that sequence, a series, because we're going to be adding the number of shares that he has together to get, or we're going to be adding to get his shares. Sorry, let's back that up. Let's just set up a sequence and not worry about a series here. So the sequence is what's important because each year it's going to be a total number of shares. So this is his initial shares here. This is basically a sub 0. It's not going to be part of the sequence, but it gives us a starting place. What we could do is we could find a sub 1. We know that a sub 1 would be 175 shares more. So 1595. We could find a sub 2 would be another 175 shares more, which would be 1770. We could find a sub 3, which would be another 170 shares more, which would be, or sorry, 175 shares more, which would be 1945. And we could keep doing this over and over and over until we get to a sub 9. Not that big of a deal to get to a sub 9. A little tedious to get to a sub 25. So what we can do instead is we can kind of get an idea. We can create a formula that gives us the values for a sub n. So a sub n, again, we're not going to use a sub 0 because that's not part of the sequence. This is the first year he works, the second year he works, the third year, and so on and so forth. So each year, basically what he's got is he's got 1595, and then the next year he's going to add 175. And then the next year he's going to add 175, and then the next year he's going to add 175. So what we have here is in the first year that he works for the company, he actually doesn't add anything. In the second year that he works for the company, he adds 175 once. In the third year, he adds 175 twice, essentially. So once here and once here, and so on and so forth. So what we can do here is we can write this out as 1595, the amount he has the first year, plus 175 times n minus 1. So we would use n minus 1 because in the first year we'd substitute in a 1, which would give us a 0 here, and that would cancel out, basically just give us 1595. So if I did this, sorry, let me show you on the calculator. 1595 plus 175 times 1 minus 1 would be 1595, which is our first term. If I did 1595 plus 175 times 2 minus 1, that would be 1770, which is our second term. 1595 plus 175 times 3 minus 1 would be 1945, which is our third term, and you go so on and so forth. So what we wanted to do here when creating this sequence expression, the general term for this sequence, is to not take a look at a sub 0, but to start at a sub 1 and then figure out what kind of mathematical computation using an addition here, because I'm adding shares, could I do to continually add 175 every year. So this would be n minus 1, because again, we only add 175 starting the second year from 1595. So now, this allows us to answer the question for A. After 9 years, what is he going to have? So 1595 plus 175 times 9 minus 1, which would be 8. So I can do this in the calculator. 1595 plus 175 times 8. I get that he's going to have 2,295 shares after 9 years. Again, this wouldn't be too bad to find if you had to do this by hand without a sequence. But for part B, it's nice to have this sequence. If the trend continues for 25 years, how many shares will he have? So now what we can do is we can use this sequence general term expression. A sub 25 equals 1995, or sorry, not 1995, 1595 plus 175 times 25 minus 1, which would be 24. So we can compute that. So 1595 plus 175 times 24 is 5,795 shares at retirement. So sequences can give us a shortcut essentially here to finding numbers that we would have to find algebraically through doing some tedious arithmetic and continuing to add. This is the final problem that we have for our SS1 notes. So SS1, again, was all about sequences and series. Most of this stuff is stuff that you did do back in Algebra 1, but it's going to set us a base level for what we can do as we start to move forward a little bit into a little more complicated applications of sequences and series. You guys will see that the homework is posted for SS1. So begin working on that homework assignment and keep a lookout on Google Classroom for information about our next Zoom session and assessment. Thank you guys for tuning in and have a great day.